Now we're live from downtown Mill Bay. Also, the other secret lesson in that story, don't be afraid to change your major or change what it is that you want to do. Honors physics to programming to chemistry, then switching into biochem because I thought I wanted to do that. I also did a work term, so I did chemistry co-op, so I got to work in the field of chemistry because I really liked chemistry in university. I found out every job in the field of chemistry I did not like. So I liked the subject. Wasn't so keen on the work. I liked lab work in university, but that requires a PhD, and I didn't really want to do a PhD. Went to biochem and then became a teacher because you can then do the stuff that I already enjoyed. Graham Zell, ex-student of Privet House, got 100% in his calculus exam, AP calculus, and he wrote it in pen. He knew he wasn't going to make a mistake before he wrote it. Went into engineering, has gotten the highest scores, I think, unbeaten by anybody ever. No, he now lives on a mountain with his wife and they take care of trees. He never wanted to go into engineering. His parents made him, and he did it because he was good at it and his parents made him, but he never enjoyed it. You do have to enjoy what you're doing. Chet, you had a question. Oh, I'll come around. I'm going to write these on the board first. So I'm going to come around and check and then assign people ones. But what I'm going to say right now is check with those around you. See if you have the same answers. So let's go. Not there. Not everybody's as tall as you, Mr. Neufeld. Does everybody have these written down? Write them down because I'm about to blank this so that we can use the board as a writing thing. PCO5, SF6, CO3 minus 2, CN minus 1, BEF2, BH2 minus, NI3, CLF4 plus. You can find instructions for these on the internet. Don't make it. It is a contact explosive and is the closest I've come to seeing a student, well, not die, but maybe rip their face off. A student was given an extra credit project. They were like the equivalent of AP and they're doing an independent lab. But instead of doing their actual lab, they found instructions on the internet on how to make nitrogen triiodide, which is a contact explosive. You throw it and it goes bang. What it didn't really tell them, because instructions on the internet are a bit wonky, is that it does that when it's dry. And when you make it, it's wet, but it dries extremely fast. So in the process of getting it from his off the filter paper and then putting it into a glass container, it dried. And while he was putting it into a cupboard, all of it exploded in the glass. And it was in an Erlenmeyer flask, so it was fairly well enclosed. And the glass, luckily, exploded almost exactly in half. Half of it went this way, one side of his head, and half of it went that way and just grazed there. He has like just missed his eye, and he's got like 3 long lines that required stitches. That's all. He's extremely lucky. If it had blown up in a different way, he would have lost his eyes. He wasn't wearing goggles. Yeah. No, it was at Stelli's. I taught there for 1 year before coming here. That's a good question, too. Yes, no, Brentwood student would never do that. Of course not. Oh, I've made it. I made our head of department at the time extremely angry. Because I made it, and then what you do is I have a long piece of paper and I spread it out on a piece of paper so when it dries, it's not all concentrated. And the intent was to take little bits off and fold it up, and then you could throw it, because I've seen magicians do that. It goes bang when it hits the ground. The problem is, as I was spreading it, it was exploding down the paper. So it was just going bang, 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 bang all the time. Couldn't stop it. And then little bits of it would land on the floor. So no matter where you walked in the lab, that lab, or here, you would go bang, 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 bang. Bang, 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 bang. It was like little tiny, like those air pockets you pop, but a little quieter. I was not successfully able to make it in a way that you could keep it for later. And I don't know how they do. So I'm going to come around and see where you're at. If you're fairly long, I may send you up to do a particular question. Why do you have a double bond there? Yeah. Well, why do you have one? Oh. You're missing it. You're literally missing it. Yep. What are you missing? So that one doesn't need a double bond. And that's a completely honest mistake, because you're missing that exact line in your notes. So you can take the double bond out and it can go back to normal. Other than that, it looked good. Okay, is everybody done writing this down? I'm going to make it a blank screen then. I'm going to walk around and take a look. Yeah, that's good. Yeah. You're allowed more than 8 if you're phosphorus or above. Yeah, you're good. Something's wrong with that one. Yeah. I don't think you've counted out your electrons properly. What is 4 times 6? 12. Okay, so you had 5, 24, and you got 32. And then you just minus 32. Ha-ha. Erase that. Don't do it that way. That's fine. But it's hard to see your work if you do it one step at a time. So first you added these 4 bonds, right? 2, 4, 6, 8. So minus that 8. And let's see what you have left. Right. 2, 4, 6. That becomes 27. 27 does equal 32. 32 minus 8 is 24. Yeah, and 6 is 24, and you do that. No, it's right. It shouldn't be. No, I know what the structure is supposed to look like. So somewhere in the accounting there's a mistake, but you have done it so well, it's convinced me you're right. I may come back to you. Check with someone, though. Maybe someone else can see it. Excellent. You're on your way. That one looks... This one seems sus. 2, 4, 6. Yeah, you got 16. And you minus 6 because you put it on there. Yeah, you got 10. You minus 6, you put it on there. Ah, that's why it is. Hold it. Erase that one. Oh, and you didn't account for the minus 2. That minus 2. Minus 2 means plus 2 electrons. So you actually end up with 18 plus 4. What's that number there? That is 22. 24 now. Restart from there. That's a good start otherwise. You look on your way. Has anybody else done the phosphorus has 1, 2, 3. You have 5 for phosphorus, right? And 6 times 4 is 24. Hold it. That only gives me 30, and you had 32. But then you add 3, 8. Yeah, no, okay, no, it's right. It's right. It's right. It's right. What am I talking about? It's right. Why am I even doubting you? Seems wrong. Oh, that's good. Yeah. Oh, you have 23? That's impossible. You have 5 chlorines, right? How many electrons are on each chlorine? 7. 7 times 5. There you go. And then, so let's do from there minus 10 from that. Hold it, what? Because I wanted to see it from the beginning. So you've got 2, 4, 6, 8, 10, minus 10 from that. And what time is it now? I don't want to be too late. Ooh, we got 15 minutes left. So if you have done one, there's lots of pens on the table. First come, first serve. You can pick one to do on the board. There should be enough for one for everybody. Yep. Okay. And then 40 minus 10 is 30. This is just PCl 5. 5, 35, 40, 2, 4, 6, 8, minus 10, 30. And then you put them all in here until you're done. So how many are you putting on each chlorine? 6. 6 times 5? There. Why are you putting those on there? Oh, how many is beryllium happy with? Oh, sorry, how many is hydrogen happy with? 2. And how many are in the bond? In the bond. Yeah, so you don't need to add any to hydrogen. Yeah. Yeah. And you always put them on in pairs. Never individuals. Perfect. This is what wrong. Yeah, carbon's not happy there. No, that looks good. Hold it. These fluorines don't look like they have enough electrons. There's something wrong with. There's 6 on these, but only 4 on those. So I don't know what's going on there in terms of your accounting. 6 times 7. If you have 6 fluorines, what's 6 times 7? 42. So you should have 42 there. So you ran out of electrons because each individual fluorine is 7, and you have 6 of them. 6 times 7 is 42? Yeah. Oh, right. You are incorrect, but for the best reasons. Oh, there's no way you could have predicted this. It's my knowing thing. So you are entirely correct for the best reasons. And now I know in the other class, someone who did get it right cheated because there's no way you'd get it right. So for your wondering for this one, if you wrote that down in the test, you're exactly right. The actual structure is that. because phosphorus didn't feel like 4 bonds were enough. And it just wanted a 5th one. Just for funsies. Seriously. Yeah. And there's no way right now you would have predicted it, because I've taught you the octet rule. I've taught you it's an exception, but I haven't taught you, like, when do you do that? And at this point, it's because it wanted to. And my brain was remembering this because I know that, and forgetting that, of course, this is the first step. So if you write this is right according to our rules, that's fine. This would be either extending, high, or emerging low. Either one of those. Or it's cheating. Because you just looked it up on the internet and wrote it down. Yes? Phosphorus is one of our exceptions. It can have more than 5, but the kicker is that it doesn't have to. It is often fine with just 8. No, we didn't. No, it's not. Sometimes the world is messy. So if I gave you this on a test, would I accept that? Yeah, I would. You haven't done enough to have that instinct to do this. But when I looked at it, I was like, my brain was like, this is wrong. And I don't know why, because you've done everything correct. And it's just because it happens to do this. And that's fine. We can allow some exceptions in our universe. The reason why it's extending, you might get this because you actually know it should and you remembered it, and like that's a thing, and you're like, aha, I got extending. Or you may have got this because you're the type of person that does this. And you just make double bonds for fun, but you just happen to give up after the first one. So you did it incorrectly, but happened to end up with the right answer. Probably emerging low is a little too cruel. That'd be developing. Or you cheated and looked it up, which is what I did just now, looking at myself, like, why am I thinking it's that way? So that is perfectly fine. Yeah, looks good. Yeah. Yeah. Do you want to do the one out there? Who has not yet done one? Okay, there's one for every member. Somebody. Chet, I was helping you when I told everybody to go up. Have you done one? Oh, dude, just start CLF4 plus. Yep. Oh, I haven't gone over them all yet, but we will. There is something wrong with that one. Come, let's go over here. Take a look. Where did you do that one? Oh, you freeze. You can't freestyle Lewis dot diagrams. Yeah, but you can do it here. Let's do it quickly. Okay. Oh, yeah, but not quite. Yeah. So just write it out, start doing the accounting. While people are doing that, let's check these. So, also tell me if you disagree, because I am also freestyling it, but my freestyling is probably a little better because I've seen them before. But this one looks good. It's got all the right numbers. That has a double bond. That seems reasonable. Carbon almost always wants to have 4 bonds, so if I saw anything with carbon with only 3, it'd be like, that's a little sus. So there we go. Boron is happy with 3. It's got 3. All the fluorines around. It looks like, now, one thing nobody has done on here is the accounting. They haven't showed me your accounting. I'm assuming you're doing that in your work then. Make sure you're including that. That one looks good. PCl 5. 1, 2, 3, 4, 5. It's got all the bonds. Phosphorus is an exception. It can have more than 8. That looks good. SF6 is almost exactly the same question. You'll find out the electrons just work perfectly to give them all 6 and you're done. So these are actually quite easy, just remembering that those are exceptions. Ooh, nice. Triple bond in the cyanide ion. This is not cyanide gas, which is just which is a different compound. But it is a cyanide ion. You can find solutions. CO3. This is good. No, that's a different compound over there. So that one's nice. Beryllium being separated. Awesome. Boron. Only 2 bonds, but it has a lone pair. That makes it happy. Nitrogen triiodide. You have the lone pair in the nitrogen. That's good. We'll go back to that one. This one here. That looks great. Oh, excellent. They didn't put any lone pairs around the hydrogen. They saw that they needed them there. That looks great. If I was to make a new question for a test, it would be so easy to take any of these and just make it like that's Cl or that's F. Like they're all the same. This is good, either one. Obviously, we've just gone over that. And now, for the piece de resistance. So where do they go? When you have extra electrons and all the other ones are full, where do you put them? The center in pairs. So just like pair there would be fine, or either others. Yeah, make them nice and dark so people can see them. Okay, Jonah. Number of electrons in sulfur. And 5 fluorines. Oh, y minus 1. What does this do? The minus 1 charge to the electrons. It adds an electron. Excellent. So 36 plus 6. 42. That means we put the center one in the center, which is the sulfur. You put all the fluorines around it. Missing one. How many electrons did I use up? 8. 42 minus 8. 34. Now, how many electrons does each fluorine need to give it an octet? No, how many does it currently have? It has 2. So how many to get to 8? 6 more. And 1, 2, 3, 4, 5 times 6? 30. So you can just minus 30. Got 4 electrons left. And then give them all their octet. Now they're all happy. What do we do? Kaylee, you had a question. You did not mishear. You caught a mistake. If this was Hogwarts, I would say like 2 points for Hope House. 2, 4, 6, 8, 10. Thank you very much. So that changes that accounting, which then makes us down to 32, which makes us only have 2 electrons left over. Where do those 2 electrons go? Double bond increases the number of electrons you have. It actually doesn't get rid or add any because you just go like that. So you cannot create double bonds with extra electrons. Yeah, you just put it on the central atom. You just find room and say, move over, baby. And you just put it there. This gives it 1, 2, 3, 4, 5, 6. What this would tend to look like is you would have sulfur, straight up, straight down. Can everybody see 3-dimensionally what I'm doing here? Hold it. 1, 2, 3, 4, 5. 1, 2, 3. I need to do this. Does this make sense? What these are coming out at you. So these are two projections like this. And these are two projections going back. The dots mean getting farther away. Okay? And this is just straight up and straight down. So there would be a fluorine and a fluorine. And there'd be 5 of them. And then one of these would be a lone pair and just be like bulging out somewhere. So the shape of the molecule would look something like this. Actually, now that I think about it, yeah, that would work. But it might be easier to see if I do this. Let's make that one go away and make it like this. And make this one the lone pair. So there's our big lone pair. This is how molecules get pyramid shapes. You don't see the lone pair. You see what it's bonded to, and it will have a crystal structure based on that particular shape. VSEPR theory is when we look at what's there and where the lone pairs are and see what shapes we get out of it, which is something we'll probably do before solution chemistry. Okay, I'm going to put it on Google Classroom at some point. We're going to have a quiz next week just on Lewis dot diagrams. It is 1:14. We are good. Yeah, just like this. Thank you. Thank you. You're welcome. Chet, was there enough? Did you get up there? Did you get up and do one? So when I said there was one per, someone did 2. So. No. But what I said is that we're going, like, this stuff gets revisited. So if you improve over time, then I don't have to count this test later. But what we need to see is a trend up. Okay? You're welcome. Sorry? Oh, right. Oh, let me go get it. I think I put it away. Thank you. Is there a red thing right there? Just have to clean up in my classroom. So, yes, Brooklyn. Sure. Okay. Now, I'm not saying you did, but it's always sus when things are heavily erased. However, solid or what was it? Yeah, no, I did. Solid and liquid. So the weird thing is, as soon as you brought it up, I could read it, and I couldn't at the time. You have magical writing abilities. Okay, everybody gets one. There. And there. I will change it. Oh, another one. Oh, 1 second. I'm just going to stop the